Hey everyone, so today we are going to talk about orthogonal complement. Okay, so see, you have already studied complement of a set, right? Suppose if I give you this R2, two-dimensional space. If I give you say x-axis, what is complement of x-axis? The upper half plane and the lower half plane. That's the complement. What is orthogonal complement? It is in the complement and it should be perpendicular. Orthogonal means it should be perpendicular to x-axis as well, which is nothing but y-axis we know. Though 0 is the common, but yeah, 0 will come. Okay, so it's complement of a set, moreover it is orthogonal to that set. Then that is what you understand or what you mean by a orthogonal complement. Okay, so in a vector space, or actually whenever I talk about orthogonality, I should talk about the inner product space. That means V is a non-empty set with plus and dot operation. That means it's a vector space and I am defining some inner product on this set, on this vector space. So once I have an inner product on a vector space, I will call this set to be an inner product space. Okay, and you let S be a subset of V. Subset, okay, I am not saying subspace. It may be a subspace, but it can be a subset as well. We define orthogonal complement as S perp, P-E-R-P, S perpendicular or S perp. It is nothing but those vector in the vector space. I will look for those vectors which is orthogonal to S. Now when we say something is orthogonal, when the inner product is 0. I have already given a lecture on orthogonality, orthonormality, some few good things. For those, the links you can find in the description. Okay, so all those vectors such that V bar dot S bar is 0 for all S in S. Okay, so what is orthogonal complement to S? You look for those vectors in the vector space which is orthogonal to each and every vector of the set S. Okay, then that is called as an S perp. Okay, now one good thing one can observe is this S perp forms a subspace. Irrespective of S, whether S is a subset or subspace, doesn't matter. Given any S, a subset or a subspace, your S perp always forms a subspace. Now again, to prove something is a subspace, what do? We need three things. The first thing is it should contain a 0 vector. So whether 0 bar belongs to S perp, that is the question. Yes. Why? Because what is inner product of 0 comma S bar? If any one of the vector is 0, then inner product is always 0 by property of inner product. Okay, one can use linearity to prove this. So inner product of 0 comma S bar is 0 for all S bar in S. So since this is true for all S bar, therefore 0 bar is in S perp. What is the second condition for a subspace? You take two vectors, let U bar comma V bar belongs to S perp. That means what? Inner product of U bar comma S bar is 0 and inner product of V bar comma S bar is 0 for all S bar in the set S. Right? This is by the definition. Now what I want to prove? I want to prove that their addition U bar plus V bar is in S perp. That is true, right? Because what is U bar plus V bar is inner product with S bar. By linearity property of inner product, this is U bar comma S bar plus V bar comma S bar. And what is this? 0 bar plus 0 bar. No, 0 plus 0, it's a real number. So addition is 0. And what is the third condition? If your U bar is in S perp, so yeah, this implies that U bar plus V bar is in S perp. Now third is if U bar is in S perp and alpha is a real number or any scalar, real or complex or rational or any element of the field. Whether question is whether alpha into U bar belongs to S perp or not. But that is also true. Why? Because what is inner product of alpha U bar comma S bar? Again by property of inner product, this alpha comes outside, alpha into U bar comma S bar. But where is your U bar? Your U bar is in S perp. Therefore, this is 0. So 0. Therefore, given a set S, which is a subset of a vector space or a subspace of a vector space V, is orthogonal complement always forms a subspace. Okay, so that's one thing that one should realize. Okay, now let me take some example and give you some hints which will help you when you play with the orthogonal complement. Okay, so let us go for the first simple example. Let me take V to be R2 and let me take the inner product as the dot product. Whenever you are playing with orthogonal complement, you should know what is the inner product, because if you don't know the inner product, you can't find the orthogonal complement. Okay, so let me take S to be, say, singleton 1 0. I want to find what is S perp. Okay, now what is S perp? Those vectors in R2 such that inner product is nothing but the dot product, such that V bar dot product with 1 0 is 0 for all element of S, but S has only one element, so I am not writing for all element of S. Okay, now what is this? What is V bar? Let me call V bar as V1 V2 dot product with 1 0. What is the dot product? V1 into 1 plus V2 into 0. So it's only V1, and what is this? Equal to 0. So what I'm getting? V1 is 0. Am I getting any condition on V2? No. Okay. So what is my V bar? My V bar is nothing but 0 V2, where V2 can be anything. Okay. So my S perp is nothing but, it is the collection of the vectors 0 comma V2, where V2 can be any real number. And what is this? This is nothing but your y-axis. Okay, so this is a vector on x-axis. Its orthogonal complement is y-axis, complete y-axis. It's a subspace. So definitely it has to be some line passing through origin, and it is nothing but your y-axis. Okay, so your S perp, your y-axis is orthogonal to, or y-axis is an orthogonal complement to S. Okay, there is one nice result actually. So if your S perp is what is orthogonal complement to S. If S is a subspace, fine. If your S is a subset, then if S perp is an orthogonal complement to S, your S perp is also orthogonal complement to span of S. That means if you take a vector in S perp, that means what? Say V bar is in S perp. That means V bar, inner product of V bar with small s is 0 for all s in capital S. If this is true, then V bar is also orthogonal to the elements of span S. Why? Now this is a homework for you. What you have to do is, your inner product of V bar comma S bar is 0 for all S bar in S. Now, how if your S bar is in span of S, how your S bar will look like? It will be some linear combination of the basis vector. So this will be some linear combination of the basis vector. Then you use the properties of inner product and use the linearity. Then this will get split. So you have V comma C1 S1 plus V comma C2 S2 plus V comma C3 S3 and so on. But V comma S1 inner product is 0 because S perp is OC to S. Inner product of V comma S2 is 0 and so on. So if you have a, if V, small vector V, is orthogonal to each and every element of S, then that small vector V is also orthogonal to each and every vector in span of S. So this is a homework problem for you. You try to solve it. If you get stuck, you can ask me for hints in the comment section. Okay, so that is one thing. Another thing that one should observe is, if your S is a subspace, then S intersection S perp is always singleton 0. S intersection S perp is always, it's not, I'm not saying it's empty. They have a common element, but that common element is nothing but a 0 element. Why so? Let's try to prove it. Let your V bar belongs to S intersection S perp. That means what? Your V bar is in S and your V bar is in S perp. Okay, now what I want to show, that V bar has to be 0. That means if you take any vector in the intersection, it has to be 0. It has no other choice. Is this 0? Yes. Now your V bar is an S perp, means what? Inner product of V bar with S bar is 0 for all S bar in S. This is 0 for all S bar. You change your S bar in S, this is 0. You keep on changing S bar in the set S, this will become 0. So when your S bar is one of the V, because V bar is also in S, so this implies inner product of V bar, when your S bar is V, then this is also 0. But what is this? This is nothing but norm of V square. But norm of a square is 0 means the norm itself is 0. But norm of a vector is 0 means the vector itself is 0. Okay. So if you have a vector in the intersection, then that vector has to be a 0 vector. So S intersection S perp is always 0. Okay. So that is one point to observe. Just see this once again. If you get stuck, you can ask me your doubt in the comment section. Another important property, or actually let me tell you that with the help of an example. Okay. Now suppose if I take V is equal to R3. Now let me take S to be the subset of R3 as 1 0 1 and say 0 1 0. Are they independent? Yes. See, always keep this in mind. Number of linearly independent vectors in the set S and number of linearly independent vectors in S perp. Addition of those two is always the dimension of the vector space. Okay. Dimension of S plus dimension of S perp is always the dimension of the vector space. Now here the dimension of vector space is 3. Dimension of S, since these two are independent, its span will be spanned by these two vectors. So its dimension will become S. I should say dimension of span of S because S need not be a subspace. So dimension of span of S, but it's okay. So this has dimension 2, this has dimension 3. So in S perp you should have only one vector. Okay. So this result helps you to at least know the answer that okay, when I will find S perp, I should get only one vector. Okay. So here what is my S perp? It is those V bar in R3. Let me call this as V1 and let me call this as V2 and let me call this as X bar. Those X bar in R3 such that X bar dot V1 is 0 and X bar dot V2 is also 0. That's what S perp is. It is orthogonal to each and every vector of the set S. Okay. Now what does the first one will imply? Your X bar is X1, X2, X3. So when you take the dot product, I have X1 plus X3 is equal to 0 and here I have only X2. X2 is equal to 0. So your X2 is 0, your X3 is minus of X1. Okay. And therefore, if you try to see your S perp, what is your X bar? Your X1 is as it is, X2 is 0 and X3 is minus X1, where X1 is any real number. This is your S perp. And you can see if I take out X1 outside, it is 1 0 minus 1. So your S perp is span of singleton vector. Okay. And that's what I told you just now, that your S perp will have only one linearly independent vector. Which is that linearly independent vector? This 1 0 minus 1. Okay. So that result, dimension of span of S plus dimension of S perp is always equal to the dimension of the vector space. Okay. So this was one hint that will help you a lot. Suppose if I go to now matrices. Okay. Suppose let me take my vector space to be a set of all 2 by 2 matrices over real numbers. Okay. And now let me take S to be a set of all symmetric matrices. 2 cross 2 symmetric matrices. I want to find what is S perp. Now what is S perp? It is set of all A in my V, which is 2 cross 2 matrices, such that inner product of A comma B is 0 for all B belongs to my set S. Okay, this is what the definition is. Now to go ahead, I should know what is the inner product on matrices. So let me define the inner product as trace of AB transpose. Okay, that's what the inner product I'm defining. So this is 0 means trace of AB is 0. Okay, now see, now this S is set of all 2 cross 2 symmetric matrices. Now this is a very large set. I can't keep on taking each and every element from this set. There are infinitely many elements. That's where independent vector helps you. So in such scenarios, you only concentrate on independent vectors. That means the basis for this set. Now we know that the basis for this set, what are this? 1 0 0 0, 0 1 1 0 and 0 0 0 1. If you don't know this, again you can see the lecture, the link you can find in the description. These are the basis for symmetric matrices. Okay, so now I have to check with only these 3 vectors. Okay, moreover, I know that dimension of M2 cross 2 is 4. The dimension here is 3. Therefore, S perp will have only one independent vector. Okay, so now if I call my A as some A, B, C, D, that means, so what I have is, if I call this as V1, V2 and V3. So I have, or instead of calling me this, let me call this as capital X, capital Y, capital Z. So I have trace of A into X transpose 0, trace of A into Y transpose is 0 and trace of A into Z transpose is 0. So now you do A into X transpose and you find the trace. You will get only A. The trace will come out to be A. Just do it. You do A into Y transpose, you find the trace. Your trace will come out to be B plus C and that is equal to 0. You do A into Z transpose, you see the trace. Trace will come out to be D. So therefore D is equal to 0. Okay. So from here what you get is your matrix A is nothing but 0 0 B. What is your C? Minus B. So all the vectors A will be of this form. What is this? This is nothing but B times 0 1 minus 1 0, where B is a real number. These are all collection of 2 by 2 skew symmetric matrices. And you can see it is spanned by only one vector. And that's what the dimension of skew symmetric is in the order 2 cross 2. Dimension is 1. Again, for this also I will post the link in the description. So this is the orthogonal complement for set of symmetric matrices. Okay, now let me take one last example and then we will stop. Let us go to the polynomial space. Let us go to the polynomial space. Okay, so let me take P2 of R, set of all polynomials of degree at most 2. I know the dimension is 3. Let me take S to be say 3x square plus 2x plus 1. Only one vector, one polynomial, one vector. Okay, therefore when you take the span, its dimension is 1. This has dimension 3. Therefore S perp will have dimension 2. That means it should have 2 independent vectors. Okay, so what is S perp? Set of all P of x in my V such that inner product of P of x with this polynomial is 0. There is only one polynomial. Okay, now what is inner product? Now let me define inner product P of x into Q of x as integration minus 1 to 1 P of x into Q of x dx. I will do for this, I will find the orthogonal complement for S with respect to this inner product. What I want you to do, you take inner product as P of minus 1 into Q of minus 1 plus P of 0 into Q of 0 plus P of 1 into Q of 1. This also forms an inner product. This also I have talked, link you can find in the description. So you find S perp with respect to this inner product and you tell me the answer in the comment section. I will find the inner product. I will find S perp with respect to this inner product. Okay, so let's find S perp. Okay, so what will be S perp? Okay, so let me call P of x as ax square plus bx plus c. I want to find ABC. Okay, now what do I get? When I do this, what is inner product of this? Integration minus 1 to 1. What is my p of x? Is this, and q of x is this. So I have ax square plus bx plus c into 3x square plus 2x plus 1 dx equal to 0. Okay, now I have to multiply this and I have to find the answer. I have to find ABC. Okay, actually this will be a big calculation for me. So just to avoid such a big calculation, let me only take x square. Idea is same, but just it will take a lot of time. For a practice, if you want, you can play with this polynomial, but just for simplicity, just to save your time, let me only take s to be x square. Okay, so I have written here x square. What this will be? Minus 1 to 1 ax raised to 4 plus bx cube plus cx square equal to dx equal to 0. What is this? This is a x raised to 5. Okay, so this is nothing but a times in 2 times minus 1 to 1 is 2 times 0 to 1. So this is 1 by 5. This integration is 0 plus c into 2 into 1 by 3 equal to 0. Okay, so what do you have? From here you have 2a by 5 plus 2c by 3 equal to 0. So this implies you can take out your 2. So your a is minus 5 by 3c. Again, you recall dimension of V is 3. S has only one vector. Therefore, S perp should have two linearly independent vectors. Okay. So what do you have? You get S perp, which was P of x. What is your P of x? Ax square plus bx plus c. Your A is minus 5 by 3 x square. Did we get any condition on B? No, there is no condition on B. Square bx plus c, where b and c are real numbers. And from here you can see that this is nothing but you can take out c outside, minus 5 by 3 x square plus 1 plus b into x. b, c are real numbers. So you can see that S perp is the span of two polynomials. Which are those two polynomials? X and 1 minus 5 by 3 x square, which are two non-zero linearly independent vectors. Therefore, dimension of S perp is 2. So yeah, this is all about orthogonal complement. If you have any doubt or if you have any problem in your mind in which you are getting stuck, you can ask me in the comment section. And if everything is clear, do not forget to like, share and subscribe. Thank you.